In this video, let's talk about exponential functions. What are they and how we can use them, particularly in business situations, but also in other situations as well. So what is an exponential function? What is it? How can we graph it? What are some of the equations that we're going to need to use later for something we call applications? So let's take a look. Well, an exponential function, the way we understand it, it's of this form. It's y equals a to the power of x, where a is a constant, which we'll call base, and x is the exponent, which is the variable. So x doesn't have to be an integer. It literally can be a decimal. It can be any number. You can even have, let's say, 2 to the pi power, and you would need a calculator to evaluate it, but that's what an exponential function is. So let's answer some questions. Is y equals x squared an exponential function by the way we defined it? Well, the answer is no, because the exponent is not a variable, and this is actually a quadratic function or a polynomial where you have a variable raised to the power. Now let's take a look at the second question. Is y equals 2 to the fifth an exponential function? So think about this one. Well, the answer is actually no. It's y equals to 2 to the fifth, which is 32, which is actually a horizontal line, so it's still not an exponential. What about y equals to 1.5 to the power of x? Yes, this satisfies the definition of exponential functions, since x is in the exponent. How do we graph? Well, there are two cases which simplify it quite a bit. There is a growth and decay. It really has to do with what the base looks like. And we can also apply shifts, the transformations that we learned earlier with polynomials and so on. So the base is bigger than 1. First of all, the base has to be greater than 0 in order for the function to be continuous. We're only going to talk about positive bases. So if it's bigger than 1, we do have growth. Let's talk about the simplest one it can be, probably, is y equals 2 to the x. And so you can substitute any base for that, but let's talk about y equals 2 to the x. Notice how at first I picked few x's as exponents, and we try to evaluate the y. If you recall some of the negative exponents, 2 to the negative 2, for example, is 1 over 2 squared, which is 1/4. 2 to the negative 1 is 1/2. 2 to the 0, if you recall, it's 1. 2 to the 1 is 2, 2 squared is 4, and so on. Let's go on. So how does the graph look like when you plot all the points? Here I plotted them. Notice how the function is increasing. It does pass through 0, 1. And something else it only has it on the left side in this case, but it has an asymptote, which is y equals 0. It does have a horizontal asymptote. So in general, the growth for any base bigger than 1, we're going to study something with a constant called e. Is also exponential growth because e is 2.718. We're going to see that constant quite a little bit later. But anyway, in general, the graph looks like this. It passes through 1 because any base to the power of 0 is 1. And it looks like this. It's increasing. It does have a horizontal asymptote, which is y equals to 0. So we do have a y-intercept for the standard graph. It's 0, 1. There are no x-intercepts in this case, and there is a horizontal asymptote in this case, y equals 0. Now, the second case is decay, where the function is decreasing. Now notice if your base is less than 1, notice I did 1/2 as an example, or you can also write it as 2 to the negative x power, which sometimes you will see it in this way. This is a model for decay. And notice the opposite situation applies. 2 to the negative second power, 1/2 to the negative second power. It actually becomes 2 squared if you flip the fraction and make the power positive. Becomes 4. 1/2 to the negative 1 is actually 2. 1/2 to the 0 power is 1, and then 1/2 and 1/2 squared is 1/4, and so on. So how does the graph look like? Well, it looks like it's decreasing, so the opposite situation is happening. And in real life situations in decay, like radioactive decay, for example, or if you have decay instead of growth, the function is going to die off over time. In this case, we do have the same asymptote, but it's going to be decreasing and dying off over time. Let's continue. The shape is the same, okay? As long as your base is between 0 and 1 or the exponent is negative. So it's very similar. The graph is decreasing. Now note, the graphing calculators, including the online graphing calculators, generally do not show the horizontal asymptote and may not continue the graph when it gets close to asymptote. Sometimes it looks like a square root function where it just cuts off. I have seen that happen, which is why hand-drawn graphs are very important for exponentials. So we're really going to study those in a little bit of a detail. But a good thing is that the shifts work exactly the same as we learn them with a quadratic or polynomials. So let's take a look at this example. Y equals 2 to the x plus 3 power minus 1. Now notice, any number that's sort of in the exponent together with the x represents the horizontal shift, whereas this number is outside of the function, represents the vertical shift. So this one is y equals 2 to the x. It's actually shifted 3 to the left, if you recall, plus, notice it's negative 3, that would make it 0, and 1 down. So the vertical shift is 1 down. So again, 3 is in the exponent, the horizontal shift, and negative 1, that looks like outside of the function, is the vertical shift. Okay, so how does the graph look like? Well, notice the way I work with the shifts. There's 2 points, actually 2 things that we need to know. One, where does the asymptote go? So notice if you have vertical shifts, the asymptote's going to move. If you have a horizontal shift, well, the asymptote moves, but it doesn't really actually go anywhere because it extends infinitely. So since we're moving 1 down, it's going to move 1 unit down from 0. So now it's at y equals negative 1. And notice how I got this point is it starts at 0, 1 right here where my cursor is at. So if you move 1 unit down, it's going to be at the origin, and then you move 3 units to the left, 2, 3. So it's going to be right here at negative 3, 0. And then from then on, I drew the growth function because it's base 2, so it is the growth. So once again, try to figure out where the asymptote goes if you have any vertical shifts, and then count from 0, 1, the common y-intercept. Figure out where that point goes. It will actually have the same exact shifts as the function does. And then figure out if you have growth or decay. Let's take a look at another example. What if we have y equals 4 to the negative x power minus 3? Now notice 4 to the negative x actually represents 1/4 to the power of x. If you recall, negative exponents, you flipped the base, which if you recall, that's decay. And it doesn't have any horizontal shifts, but we do have a vertical shift. It's shifted 3 down, notice, because of the negative. So how would we graph it? So notice I graphed, again, I try to figure out where the asymptote goes. It goes 3 units down, right at the negative 3. And then the y-intercept went from 0, 1, it went 1, 2, 3, 3 units down. It did not move left or right, so it's actually at 0, negative 2. And then we have decay. And that's all to really know about the graphs. Equations, we're only going to cover very simple equations. If we can bring them to the same base for now, because later we're going to need logarithms, which would be the next section. What if we have 3 to the power of x equals to 81? What can we do? Well, let's bring them to the same base. Notice 81 is actually 3 to the 4th power, which is, well, it's 9 squared, which is 4 3s, 3 times 3 times 3 times 3. And so because they're the same, now we compare the exponents. So it's x equals 4. So the answer is 4. Now similarly, what if we have 3 to the x equals 1 over 81? Same idea can apply. It's 3 to the x equals 1 over 3 to the 4th power, which we can write it as a negative exponent. 3 to the x equals 3 to the negative 4. So you may guess x is equal to negative 4 is the answer. Now let's take a look at some, one application we'll do in this section is interest, compounding interest. You may recall from your algebra courses, its amount equals to principal times 1 over 1 plus rate over n, the number of compoundings, to the power of nt. So p represents the principal, the original amount, r is the rate, we write it percent, or as a decimal actually, t is the time, and n is how many times you compound per year. So you have annually, semi-annually, quarterly, monthly, and continuously compounded interest. It's when n goes to infinity. Doesn't mean you get infinite amount of interest, however. There's something from calculus we'll find out it has to do with e, actually, or the limit. Maybe we'll see the limit later. And the equation we'll use is a equals p e to the rt power, or sometimes it's called PERT. Well, that's kind of what it looks like. Same idea. P is the principal, R is the rate, T is the time, and E is the base, which is usually found in your calculators, but it's 2.718 and so on. It keeps on going. So how do we find interest? If it's 10,000 invested for 5 years at 4% interest, so we have different amount of compoundings. Note how I wrote R equals to 0.04, and then we just plug in. If it's annually, it's fairly simple. N equals 1, so A is equal to 10,000 times 1 plus 0.04 to the 5th power. Notice the way I write it is exactly the way I plug it into my graphing calculator, so you don't actually need to do it separately. And this is what I got rounded to the second decimal place, the 100th decimal place, 2 decimal places. So this is what I get, $12,000, about $12,000. But the question asked for the interest. How you can find out? That's the amount minus the original principal. So I'm getting $2,166.53. Quarterly, same kind of idea. Notice again, I wrote it specifically how I plug it in a calculator. And same kind of idea applies. Monthly, again, same idea. I just used 12 for the n. And continuously, again, same idea. I used e to the x power, where if you're using TI-83 or TI-84, it's second ln, and you can find it on most even scientific calculators. And here is a quick one on population growth. What if the equation is given? Just simple population growth example. If you have A of t, and t is the number of years since 1960, world population was about this amount, 3686 million in 1970. This was given, actually wasn't given, this was an actual information. How closely does the function approximate this value? So it's 10 years passed since 1960, so that's why I put t equals 10. So if I plug it in, and we'll find out how our model approximates this information. Well, I rounded to the nearest whole number, which I got 3660 million, and notice how it's pretty close to 3686. Yes, it's about 20 million difference, but it's still fairly close to the actual population. And then we use the same amount to approximate it, 2000. I used t equals 40 since 1960, and again I plug it in and I got 6,022 million, and the actual number was 6,115. Again, it's fairly close, all things considering. Remember, the model's only approximated, so it's not going to be exact. And estimated in 2015, we can plug in t equals 55, and I got 77.25 million. And that's it.